Okay, hi everybody. Thanks for coming out to the final theory seminar of the semester. I'm very excited to have Anson Kahng today. Anson is an assistant professor at the in the computer science department and also at the Gergen Institute of Data Science at the University of Rochester. He completed a postdoc with Nisarg Shah at the University of Toronto and his PhD at Carnegie Mellon, working with Ariel Prokacha. He's done some very cool work in sort of like automating ethical decision making and sort of theoretical paradigms to try and like understand how to aggregate people's preferences and solve problems and things like democracy and so on. And with that, I'll let Anson take it away.
All right, thank you for the very kind and slightly overblown introduction. I hope I can live up to the hype. But yeah, so my name's Anson Kahng. I'm from the University of Rochester, and today I'll be talking about my work automating ethical decision-making via something called virtual democracy. And so just as a quick note to before I start, this actually dovetails very well with Alex's talk from last week. So we actually started on kind of the same types of projects, and this will be talking about, I'm not sure how much he covered about virtual democracy and food rescue, and in particular our work in Pittsburgh, but this will kind of, if you watch these talks, I think my talk first and then his, it might give a more holistic picture of how we both came to work on kind of the same things. But I want to start off with 3 goals for today. The first goal will be to introduce something called virtual democracy. And hopefully by the end of the lecture, you'll be able to say exactly what it is, why we might use it, and potentially poke some holes in it because many people often try and often succeed. We're going to study in particular the theoretical foundations of virtual democracy. This is kind of fitting for a theory lunch talk. And in particular, we're going to look at virtual democracy from the lens of voting theory. So voting theory, just as a very quick overview, is basically saying how do you aggregate preferences of heterogeneous populations in order to come up with one course of action or one decision on behalf of the entire population. And the third goal is to basically look at all of this holistically through a case study in food rescue. So I will actually kind of go about these goals all together. They won't be kind of presented one at a time. And over the course of the talk, I will use this food rescue paradigm to introduce, motivate, and study virtual democracy. OK. So I really want to quickly go over my research before diving into the specific talk, just to kind of give you all an introduction to me. And so as Alice mentioned, I work on the intersection between computer science and democracy, often through the lens of voting theory or voting rules. And crucially, we view this relationship between computer science and democracy as a two-way street. So maybe the more common way of relating these two fields is trying to decide how we can use tools from theoretical computer science and artificial intelligence to make democracy better. So this is by proposing, evaluating, designing, and revising like new democratic paradigms. So things like liquid democracy or participatory budgeting. These are all things that I've kind of worked on in the past. But this talk is really about the kind of reverse direction. And this is potentially less obvious to people. But basically, we can use ideas from democracy, in particular kind of the wisdom of the crowd and voting theory, in order to help solve hard problems in theoretical computer science and artificial intelligence. Basically, places where optimization doesn't have a clear objective or where we're kind of unsure how to like actually phrase the problem, we can kind of defer to the wisdom of the crowd and hopefully use things in democracy to kind of help us solve these problems. And this is exactly where the topic of today comes in. I'll be talking about something called virtual democracy. And I guess as an overarching framework, I want you to keep in mind the fact that we are trying to apply principles that first cropped up, at least in recorded history in like ancient Athens, to help solve hard problems that exist today. OK. And so as I mentioned, I'll be going through this whole talk using the motivating example of a problem called food rescue, in particular focusing on our collaboration with an organization called 412 Food Rescue, which is a nonprofit in Pittsburgh. But first, in order to introduce this problem of food rescue, I have to introduce the dual problems of food waste and food insecurity. So food waste is basically just disposing of food that was never eaten. Right? And this is a big problem in many developed countries around the world. In particular, in the United States, I think the statistic is close to 40% of all food that is grown or produced in the US is thrown out without being eaten. This is over 60 million tons of food a year and costs over $200 billion. And the cost is not just monetary, it's actually environmental as well. So I think the statistic is something like 50% of all the land, 80% of all the water, and 10% of all the energy in the United States goes toward food production. So wasting almost 40% of the food produced is very costly environmentally as well as economically. And you might think that, well, if we're throwing away so much food, this might just be because we have too much, and so everyone is kind of well-fed, and so we just are disposing of the excess. But despite all of this waste, despite throwing away 40% of all the food that we produce, some statistics say that as many as 1 in 7 Americans is so-called food insecure, which means they don't have consistent access to kind of healthy, affordable food. And this includes, I think some estimates say as high as like 15 million children, right? So I think 1 in 5 children in America has experienced like periods of food insecurity, which is shown to be like very bad developmentally, right? Like both in terms of like physical and kind of emotional maturity. Like this, not having consistent access to food really takes a toll on people as they grow up. And so you might think that, well, we have these two problems of food waste, where we're throwing away food, and food insecurity, where people don't have enough food. And you can kind of put these together into the paradigm called food rescue, where basically the goal is you want to redistribute food that would have been thrown away and give it to people who are food insecure, right, who don't have like consistent access to healthy food. And this basically exactly targets this asymmetry between food waste and food insecurity. And there have been many organizations, both on like a national and local level, that are trying to do this exact problem, right? Like try to funnel food that would have been thrown away into food pantries or housing authorities where they can redistribute the food to people who actually need it. So nationally, the biggest organization many of you might have heard of is something called Feeding America. And this is basically a big network of food pantries that redirects food waste to combat food insecurity. And they do this by a combination of like national and local level organization, where they have particular pantries in cities, and these pantries are kind of, I guess, cared for by people who belong to this organization. And they try to basically help as many people in America as possible get access to food. We are going to focus on food rescue at a more local scale through something that was established in Pittsburgh maybe a decade ago called 412 Food Rescue. And this nonprofit basically routes food donations that they get via phone orders from places like grocery stores or restaurants or bakeries. And they route them to recipients, which you can think of as food banks, housing authorities, other kind of food pantry-esque distribution hubs for local neighborhoods, through a network of volunteers who are mostly retired people who are willing to give back to their communities. And so they spend a couple of days a week driving food donations from donors to recipients. And so how it works, a little bit more under the hood, is that it really comprises 4 groups of people. I will call these groups of people stakeholders in the process throughout this talk. And I've depicted 3 of them here. So there's donors on the left. These are grocery stores or co-ops or restaurants. And they have excess food that they will have to throw away. But they can call up 412 Food Rescue and tell them that they have a donation, right? Once the employees at 412 Food Rescue get a call saying that there is a donation, then they identify a recipient that they feel should get the food, right? And these recipients, as I mentioned before, are things like food banks or housing authorities. So you can think of these as like central community food kitchens. And then once the operator at 412 Food Rescue identifies a recipient, then the 4th stakeholder group comes into play, the volunteers. So they will dispatch a volunteer. The volunteer will drive over to the donor, and then they will get the donation and drive it over to the recipient. So in total, there are kind of 4 groups at play here. There are the donors who kind of come into the system with excess food. There are the food rescue employees who have to, number 1, identify a recipient, and number 2, coordinate a volunteer. There are the volunteers themselves who pick up the food and actually transport it to the recipients. And then there are the recipients, who are kind of the end of the line of 412 Food Rescue's pipeline, but then who go on and actually give food to people in their local neighborhoods. Okay, I'll pause here for any questions about how this works because it'll be kind of important going forward. And, oh, sorry, question? Oh, okay. And if you have any clarifying questions, just feel free to interrupt. It won't disrupt the flow of the talk at all. Okay. So the way that 412 Food Rescue currently works is they have one person in a room per day who makes all donation decisions that happen. This is a big task. So there are hundreds of phone calls a day. Their list of recipient organizations is growing over time. I think as of last year, it was at over 400 recipient organizations. But at this rate of growth, it'll be over like 500 pretty soon. And this employee has many operational constraints on how much time they can put into deciding who actually deserves each donation. So they have constraints like, which recipient will pick up the phone fastest, because the faster I can get this donation sorted, the faster I can get on to the next one, right? They will also consider things like distance, right? They want to basically pack as many trips for a volunteer into their shift, so they want to choose recipients that are close to donors. They might also have kind of implicit favorite recipients, like those that they have good personal relationships with, or those that they know will always pick up the phone when they're called. And so they do have these implicit biases with respect to which recipients they will actually think of, even as potential recipients for food. And the issue here is that based on these operational constraints, the operator, as they're called, will often make convenient decisions instead of fair ones. Right, where we can define fairness in quotes because I haven't actually defined fairness in any rigorous sense yet. And we want to instead, in an ideal workflow, have an automated decision-making process that takes all of the burden off of these human operators who are prone to basically like being so stressed they can't really think about who should get the food. In practice, we won't quite automate this entire thing because we want humans to have the final say in whether or not a decision is still fair to them. So we'll build a decision support tool that I'll introduce toward the end of the talk that basically provides a suggestion of where to take the food. These suggestions are going to be in the form of ranked lists, so maybe they'll initially respond with the top 10 recipient organizations they think you should give the food to. If you prompt them, they will continue this ranking until they rank everything in the system. We also want this workflow to be democratized in the sense that we want to consider the opinions of more than just the 412 Food Rescue employee who is making the decisions on that particular day. So right now, there's only one person per day making all these decisions, but we want to include input from everyone who is actually in the system, in particular, everyone who is a member of the 4 stakeholder groups. So the employees, recipients, donors, and the volunteers. And lastly, very importantly, we want this to be transparent, right? We want people to be able to kind of audit the system, and in order to make them trust the recommendations, they have to understand how these recommendations were made, right? So we want basically something that checks all of these 3 boxes of being automated, democratized, and transparent. Yes?
Just a quick question about what is in scope and what's not in scope. Is this just ranking them? Like, one of the factors being whether the recipient is going to pick up the phone. Is this actually calling people, or is it just helping people call people? Yeah.
Great question. This is just helping people call people. Okay. Yeah. So it's not actually doing any of the calling yet. It's just saying, well, we think that based on a bunch of factors I'll introduce later, we might suggest you give it to this one if they are open and pick up the phone and all these other constraints. Yeah. Okay. So maybe one way of thinking about this is that the decision support tool will give you potential allocations, and then you can do the work in actually realizing these allocations. Yeah. Okay. Any other questions? All right. So I'm going to start off with sorry. Yes.
Is this problem being solved online in terms of each time there's food to be given out, there's a decision-making, automated decision-making process happening, or given some amount of food we have, we want to give it to X amount of donors at once?
Great question. This is online. So this actually leads me right into this straw man. So it's a great question. But basically, we want to make a decision at runtime every single time a decision comes in. So the workflow is, as soon as you get a call from, let's say, a supermarket saying we have a bunch of bagels, the decision support tool will say, OK, we suggest you donate it to like these 10 places. OK. So I'll start off with a straw man here. And I'm just going to say that defining what constitutes a fair allocation of food is very hard, right? People have different ethical preferences about what they think is kind of a reasonable allocation of a food donation to a recipient. And so we want to basically punt on this and just let the crowd decide, or let democracy decide. And a very naive way of doing this is asking participants to cast a vote every single time a decision needs to be made, right? So every single time 412 gets a phone call, we'll just say we have a panel waiting, and they will cast a vote about the complete ranking over all 400 organizations where they think the food should go. And so let's say the donor is a supermarket, Giant Eagle, and they have a donation that consists of turkey, broccoli, and carrot. And then they basically elicit the opinions of a bunch of other people, other stakeholders in the system, right? So it could be other donors, it could be the recipients, it could be the volunteers, it could be the people at 412 Food Rescue, like the employees themselves. And each of these people get to vote, and they will produce some sort of ranking, right? So this is a particular ranking. Let's say this is of the food rescue employee. They say that, oh, given this donor and this donation, I think that we should give it to the food bank. And if not, then the Meals on Wheels, and then et cetera, kind of down this ordered list. And then at the end of the day, you'll do some sort of aggregation in order to get a final ranking. So one main issue, which you kind of brought up obliquely, is that if you were to do this, you have to consult participants every single time a donation occurs. So this is 100+ times a day. You have to get votes from people. And additionally, these votes are kind of very complex, right? Because you have 400 potential recipients, and you're asking everyone to give a complete ranking over all recipients for that particular donation. And the way that we can leverage kind of tools from voting theory and computer science here is that we want to be able to predict how people would vote. And instead of asking them to vote every single time, we can just ask like our predicted models or our models for predictions on how these people would have voted had they actually seen this particular donor-donation pair. OK. Oops. This skips a little. OK. And that brings us to the framework that I've been talking about today called virtual democracy, where basically we want to learn models of people and then let the models vote. And broadly, we can break this up into 3 different steps. The first step is what we'll call data collection, where we're basically trying to get information about people's ethical preferences. The second is using this data to learn models of people and let these models vote over where they think the food should go. And the last part, and the kind of most theoretically interesting, is the aggregation step of, given a bunch of predicted votes, how do you aggregate them in order to provide some sort of like theoretical guarantees on the final output? And you can think about this as like the first 2 steps broadly constituting machine learning, and the third step being social choice. OK. If you think this is a little dystopian, you're not alone. Isaac Asimov actually wrote a book called, or a short story called Franchise, where the premise is that in order to elect the next president of the United States, a very smart computer called, I think, Multivac, basically selects one person at random, talks to them for a while, and then uses their information to simulate exactly the entire election and then choose a president. Right? So this kind of idea has been around for a while. It sounds a little bit Black Mirror, but we promise it's not actually supposed to be that scary.
Question, please.
Yeah.
Are we making the assumption that when somebody makes a donation, it has to go to one recipient instead of taking the chicken and giving half of it to one recipient?
Yeah. So basically, we're assuming these are atomic donations. We're not allowing any splits. If we could, I think the problem gets significantly harder, and also volunteers become significantly more overloaded, right?
What does the organization actually want?
Oh, the organization just wants to, I think they want to rehome all the donated food in like the most efficient way, which means the They're okay. There's kind of two things. They want to like have all the food be consumed, right? And they also want to not like neglect particular organizations. Yeah.
Because it seems to me like if I'm working there, hypothetically speaking, and I get some bread from one donor and some chicken from another donor, I actually want to create meals. So I want to combine the bread and the chicken and split it, divide it among different recipients. Instead of
Right.
giving all the bread to one recipient and all the chicken.
Yeah. That is a good point. I think if we allow for combinatorial things, it gets a lot more complicated. But I will also point out that the recipients are kind of food pantries themselves. So if they kind of get even donations from not only 412, but like other local organizations, then they can kind of still have like a well-stocked pantry for their users. Sure. Oh, capacity constraints? We are assuming no, because all these places essentially are always running low on supplies. So we're assuming no for now, but maybe in practice, yes. And also, the recipients in practice will tell us if they have capacity for a donation. So it's kind of self-limiting in that way. Okay. Other questions? All right. Oh.
I guess the model assumes static feature.
I'll get into that in a little bit. It's not quite static. It is responsive to what it did in the past. Yeah. Okay. These are all great questions, though, so keep them coming. All right. So I want to start off with these steps in order, starting with the first one, data collection. And just as a kind of intuition about the step, the only thing we're doing is we're asking stakeholders pairwise comparisons over where they think food should go. So all these comparisons will be of the form, you have a donation, and then the profiles of two recipients. And all the person is doing is choosing which one they feel like should get the food. So these are kind of the simplest types of comparisons we can ask. So in this step, we have a collection of, I think, 23 people in total. They range from people in all four stakeholder groups. There are fewer employees because there are few employees at 412 Food Rescue. There are more of the others because there are more donors, recipients, and volunteers. And we asked them pairwise comparisons that look something like the following. I've cut off a little bit at the top where it actually says some information about what the donation is. We basically have more common and less common donations, where the more common donations are things like bread, less common donations are things like fresh vegetables or fresh meat. And we have a bunch of features that we collect from each of these recipients. And these are based on work by our collaborators who are HCI researchers who used to be at CMU. Now the lead researcher, Min-Kyung Lee, is at UT Austin. But they identified things like recipient organization size, like travel time, food access, last donation, income level. Like all these things are what came out of a very comprehensive survey about what people in this particular pipeline, so in the ecosystem of 412 Food Rescue, thought about when they considered what constitutes a fair donation. So here are the features kind of laid out in a little bit more clarity. And I want to stress a couple of things that might go to your point about whether this is like static or dynamic. So some of these are definitely static, right? Like the organization size doesn't change, the level of food access doesn't change, that's just like the neighborhood they're in. The income level of the neighborhood and the poverty level of the neighborhood don't really change between censuses, right? So all of these things are kind of fixed for like 10 years at a time. However, there are some things that are dependent on the relationship between the recipient and the donor, right? So the travel time differs based on which particular recipient we have and which particular donor we have. And there are things that are kind of recipient and history dependent, right? Like when was the last donation, and what is the number of donations received in the last 3 months, right? And there's even one feature that is only donor determined, right? It doesn't depend on any of the recipients. It's just basically, is the type of food donated common versus less common, right? So these features kind of encompass a large swath of basically all information that we could possibly want when we are talking about like making a fair food donation. Okay, questions about these features so far? Okay, oh yes.
When we talk about type of food donated, is this binary like common or less common?
Yes. just binary. Yeah. And a lot of these are, I guess, ordinal or nominal type data. Like the organization size is basically like 6 or 7 levels of like size, right? So is it less than 50? Is it between 50 and 100, 100 to 200, et cetera? Levels of food access and income level were also discretized to maybe 1 of 5 or 6 different levels. Yeah, just all in the effort to make this a little bit easier for people to do these comparisons. Okay. So after we have all these pairwise comparisons, we then have to do some learning, right? And so this step I'll define as kind of 2 things at once. The first thing is we want to learn some model of these stakeholders' ethical preferences. And the second thing is we want to let these models vote. So you can think about this as like learning and then predicting. So when we make this, I guess when we start this step, when we try to learn predicted votes, we're going to make a pretty strong assumption that each participant will have a random utility for each alternative. And this random utility will just be a function of the alternative's features. Yes?
So in the
Yeah.
first step, did you ask these employees to rank them, or you just collect the data based on history?
We just ask them for pairwise comparisons. So we generate like a bunch of these at random, and we just say, which one do you prefer? Yeah.
I was just wondering, why don't you just look at the history data and then, like for example, when a new donor comes in, and then you have already all the features available, and then they pick one of the recipients, which means that they prefer this one over all the other recipients. So that kind of already gives you the preference.
Okay, I see. So this is a good suggestion, but there are a couple of issues. The first is that if we were to look at historical data, we're only getting the preferences of exactly one employee at a time, right? So that's the only thing we learn. And we're also trying to get away from any sort of implicit bias that they have. And one very interesting thing that we learned when talking to the operators is that they know they are making unfair decisions. They do not like the fact that they're making unfair decisions, but they feel like constrained in the amount of work they have to do. And so they just repeatedly call the same like 10 places over and over because they know that they're kind of bigger, or they know they pick up the phone more often. And so they told us very, very explicitly to not look at their previous data as like a reflection of their own ethical preferences. It was just kind of like, you know, they were doing the best they could at the time, but they realized that wasn't fair. Yeah. And we actually, I'll show a slight comparison to historical data at the end of this talk. Yeah. Okay. All right. So in the learning, we're basically going to try to learn some sort of like random utility for each alternative that we are going to specify as a linear utility, right? So basically, the reason that we're using such a simple function is because we have very little data per participant. So we have 23 people taking these surveys, and each of them only could do between 50 and 100 comparisons before they got very tired. And yeah, I sat down and did a bunch of these comparisons, and I barely made it to 50. Like these get very like mentally taxing after a while. We did allow them to kind of revisit the site and do more on their own, but very few of them actually went back and did more. And so, yeah, I'll say we tried a bunch of other stuff, but most of it did not work as well as this very simple like linear model. And just to kind of put this in perspective, so for each recipient, so in this case, the recipient is the YMCA, we are going to learn some, they're going to have like assigned to them some sort of feature vector, right? Like given a particular donation, there's going to be some sort of like, you know, distance, last donation, total donation, and then the same like 4 fixed recipient specific features of the size, food access, income level, and poverty level. And we basically want to learn this weight beta for each participant, where we're basically saying that the goodness of the fit for, you know, this particular, or I guess the goodness of the YMCA in the eyes of the gray agent is just going to be the dot product between these two vectors, right? And so that means in particular that for a participant, if you have a higher weight on a feature, that means you kind of care about them more. And for the recipient, we've kind of normalized all the values such that higher feature values are kind of better, right? So low distance, high poverty rate, low income, right? Okay. And so basically, after this kind of naive learning step, we have for each participant, whenever a donation comes in, they have a predicted ranking over all alternatives where they rank by the dot product of like their particular beta vector with the feature vector for that alternative. So kind of visually, this basically says that we learn, and then we have these models predict what the blue and the green agents would have said, right? And empirically, we observe that the pairwise accuracy, so basically the probability that any sort of model orders any pair of alternatives correctly, is roughly 90%. Right? So they're kind of good pairwise, but they might not be good complete ranking-wise.
I have a question about the model.
Yes.
It seems to me like some of these variables should be combined together. Like for instance, the population size of the, I don't know, let's say quarter times the poverty rate, because that indicates like total poverty. So I feel like maybe the linear model is like poverty in a 10,000 people zip code the same as 100,000 people zip code, you know. There could be some benefit in some of the nonlinear interactions.
Yes, that's a very good point. I will say that we looked at this a little bit when we looked at like polynomial utility functions. So we did try to look at like, you know, pairwise combinations of these types of variables, and it just did worse because we didn't have enough data. Right? If we had more data, I would imagine that doing this would, you know, work much better than a simple linear utility model. But yeah, we did try it, and we just didn't have enough data to make it work. Yeah, that's a great suggestion. Okay, so we have this you know, predicted output, and we have this probability that the pairwise comparison between any two ranking or any two alternatives in the ranking is roughly correct with 90% accuracy. And so basically, after the end of the day, you have this flowchart of you have people who come in with a particular like unobservable true ranking, and they kind of get put through this like data collection and learning step in order to be turned into like a robot that like predicts their rankings. And this robot is kind of accurate overall, but it definitely does still make mistakes, right? And so after getting these predicted votes from each participant, now the question is, well, how do you start aggregating them, knowing that there are some mistakes that are made in this whole like data collection and learning process? And that's where the kind of the theoretical part of this work comes in the aggregation step. And the question is really, how do we aggregate all these predicted kind of noisy votes in a way that is consistent with the unobservable good votes or like true votes that we can't observe? So the main question here will basically be trying to satisfy two things at once. The first thing that we want is we want this aggregation method to be robust to machine learning errors. And all that means is that we want voting rules that are likely to output the same ranking on the underlying unobservable preferences and the noisy predicted votes. So in this diagram, you have a bunch of like true preferences. If you put them through a voting rule, you'll get something. We want that to be the same output as if you put their noisy learned preferences through the same voting rule. Right? We just want these two things to be the same. And as I mentioned in the very beginning of the talk, we also want this to be explainable to users of the system. Right? We don't want it to be such a complicated process that they don't know what it's doing and they therefore don't really trust it. Okay. And so our model basically consists of some transformation of hidden votes to observable votes. So right now, I'll let sigma star be these true rankings, like the participants' real opinions. And after the data collection and learning steps, we get some sort of like predicted opinions. Right? These are the noisy opinions, which are just some sigma. Oh, yes.
To understand what's the true ranking for one particular participant, you didn't tell us how you're going to combine it.
Sorry?
I understand what's the ranking
Yes.
for one particular voter.
Yes.
You didn't tell us, how do you combine the ranking?
Oh, that's what this whole step is about, right? So we've kind of only looked at so far individual opinions. And now this next step is basically asking, like, what voting rule should we use to combine all opinions?
I know, but
Yeah.
you start from the hidden one.
Mhm.
I don't even know what's the ideal. What's the hidden?
Oh, maybe at the end of the slide it'll be a little more clear, but yeah.
You haven't gone through aggregation yet, right?
No. This is all warm up to aggregation. Yeah. Okay. So we can assume that these hidden true preferences, we'll never see them. They are some sort of complete ranking over all recipients, right? So they're really, really long complete rankings. And we will model the learning step with something called Mallow's noise, which is a very common noise model in social choice. And Mallow's noise, you can think about it as being Gaussian noise for rankings. So I have a formal definition over here, but in the interest of time, it's probably easier to just look at this curve. And basically, a Mallow's model takes in two parameters. The first is the mode ranking, this like sigma star. And the second is some phi that is a dispersion parameter. Like phi basically says like how sharply peaked this Gaussian is. And basically, the probability that you draw a ranking decreases exponentially quickly in the distance between these two rankings, where the distance is defined as essentially the bubble sort distance between the rankings. So yeah, you can think about the Mallow's model as Gaussian noise. And after applying the Mallow's model to each of these true rankings, you get the observed rankings over here, right? This is just modeling what happens after the first two steps, the machine learning part. And now the goal here is we want to find a voting rule F such that F applied to the unobservable hidden rankings is exactly equal to F applied to the noisy rankings with high probability. Right? So all we're going to be doing now is looking at potential voting rules and deciding whether or not they fit this criteria of being basically like self-predicting or robust to Mallow's noise. Does that help clear up some of the? Yeah, okay. Yes.
This may not actually be relevant, but the way that you've written these preferences they're definitive, right? They're not dependent on the donor, but the preferences can change depending on where the fruit's coming from, right?
Oh,
sort of abstracted away.
sorry. These are meant to be. They're meant to change every single time a new thing comes in. So basically, each of these hidden preferences are preferences over the pair of donation or donor, donation, and all recipients. Yeah. So these are all instance dependent. Yeah. Okay. So we basically studied two main classes of voting rules. The first is an example of something called a positional scoring rule called the Borda count. And the second is a very large class of rules called pairwise majority consistent, or PMC rules. I'll go over these in the next couple slides. But we might not have time to go through the negative result that I wanted to. So the Borda count is pretty simple. Basically, voters give points to alternatives based on how much they like them. So they give 0 points to their least favorite, then 1 point to the next last favorite, and then all the way up to m minus 1 points for their favorite, where m is the number of alternatives they have. Alternatives are then ordered by decreasing score summed over all voters. So if you have this particular example with 3 voters who think the ordering should be ABC, and 2 voters who think the order should be BCA, well, then the score of A is basically 2 points every single time it's in first place, and 0 points for the 2 times it's in last place. So it gets 6 points total. B gets a total of 1 plus 1 plus 1 plus 2 plus 2, which is 7 points. And C gets very few votes, or very few points, because it's only in second place twice, right? So the overall ranking under the Borda rule is going to be B, and then A, and then C, just in order of decreasing score. In contrast, PMC rules are a little bit more complicated, and they rely on something called a pairwise majority graph, where this graph basically has 1 node per alternative, and there is a directed edge from a node X to a node Y if and only if over half of the voters prefer X to Y, right? So basically, this is all about head-to-head comparisons between different alternatives. And a voting rule is PMC if it outputs the topological ordering of G when G is acyclic. If G has a cycle, it doesn't have to do anything. It can do whatever. And there's some examples like the Kemeny rule, Copeland's method, if you've heard of these voting rules before. But let's just look at what happens on the exact same profile as we looked at on the previous slide. So in this case, when we draw this pairwise majority graph, we note that A beats both B and C in a pairwise comparison, right? Because over half of the voters prefer A to both B and C, right? So there's an edge from A to B and an edge from A to C. And there's also an edge from B to C because every single voter likes B more than C, right? So this is an acyclic graph, and the topological ordering there is A and then B and then C, right? So even on a very simple profile like this, Bordas said BAC, and PMC rules say ABC, right? So they can differ even for very simple constructions. And the main results, I'll put them on the screen very informally. But basically, we show that the Bordas count is kind of robust to this type of mallow noise. So even if the difference in the true Bordas scores between two alternatives is small, Bordas swaps them with only exponentially small probability. So this probability goes to 0 very quickly. And in contrast, PMC rules are very much not robust under Mallow's noise in the sense that there always exists a profile with an acyclic pairwise majority graph in the true profile, where the noisy profile has with high probability a different acyclic pairwise majority graph. Okay, so here basically the takeaways are we should use Bordas count for virtual democracy, and we should not use PMC rules for virtual democracy. And I would, oh yeah.
Sorry, so in the more formal version of the second one, is this saying that like you give me any PMC rule and I can always demonstrate that it's not robust, or is
Yes, any PMC
it's
rule.
not just that
Yeah.
all you know is that it's PMC, that it's not necessarily robust? As in like something which is implied by this is that the Kemeny rule is not.
Yes, exactly. Kemeny is not robust. Copeland's not. Yeah, any PMC rule is not robust. Okay. In the interest of time, I think I'll have to skip the negative result sketch.
Okay,
But, yeah.
So I guess there's a very like sort of brittle sense of being robust to noise here, and that you're asking for exactly the same kind of order
Yes.
as you started with. If I relax this to the outcome can be approximately in some sense similar to the first thing, is there more hope?
I think if you ask for approximately, then most rules are pretty robust. And so we do need the kind of brittle exactness to get the separation. But yeah, if you want to, let's say, only have some small number of swaps, like bubble sort swaps between the two distances, I would imagine that you could probably get both of these to hold. Like you could probably get like a positive result for like positional scoring rules like the Bordas count, and then a negative one for kind of pairwise majority rules. But it'd be a little more complicated. Yeah. Yes.
So when you say small in the for the first theorem, does it mean 1 or does it mean
Okay. That.
0, 1?
Yeah. There's. Okay. I'm actually hiding some complexity here. So recall that I talked about the Mallow's model in terms of this dispersion parameter phi, right? In our paper, we actually use a different way of like looking at the probability of swaps. We use a notation of beta and kappa, where basically we're saying what is the probability of swapping things that are kappa distance apart. And there is a relationship between this beta kappa version and the phi version, but it's a little bit complicated. I think the overall thing to note is that this positive result is fairly strong. So even when the difference between the true Bordas scores is, I think, I have to check, but I think if it's still like very much sublinear, then you can almost always get the right thing.
So the reason why I'm asking is I feel you want to when you make claims like this, even at a very high level, you want to make sure they're compared on the same ground, right? To be
Yes.
fair. In the sense that maybe your construction for the second bullet are instances where they're very close to tied, and then you can flip the outcome of PMC rules. But for the first one, if you require, let's say, a difference in Bordas score of 0.01n, that's relatively small, but it's still like may not be the same ground that you're using for the second.
Yeah, so I'm happy to talk about this more offline. So these two things are not, in the strict sense, like directly comparable, but the negative result is kind of still strikingly negative in context of the positive one. Yeah. Okay. Yeah.
is a history of, a lot of studies on very different ordering.
Mm-hmm.
For example, if the whole thing changes, if you assume that the error of the noise is proportional to the actual difference in order. So that is very little noise, which is reasonable in real life. So if I compare two things that are relatively close by, there's more probability of an error than if I compare something that are very far away.
Mm-hmm.
So there's there are a lot of papers. But I want to comment about something else, which is more about the foundation. So you set up everything as in the beautiful setup of democracy. But in democracy, the population is crucial. And here, who votes, or the number of voters, you didn't explicitly say that, but it seems like you give votes according to how many participants there are in each group. So for example, if there are a lot of donors and a few people get the donation, then somehow the donors have,
That's a very good point.
And
Yeah.
maybe the volunteers should have much more say because they volunteer.
Yeah.
So,
we actually don't weight everyone equally, and we actually had participants kind of do a meta analysis of how much voting weight each group should get. And what came out at the end was the recipients and the employees get a lot of weight, the donors and volunteers get less. But it was kind of 40, 30, 20, 10, like roughly in that proportion.
This was built out of which source?
Out of, sorry?
Okay. You got this weight
Yes.
through which process?
Oh, deliberation with everyone in a room.
Okay.
Yeah.
So you started with equal vote,
Mm-hmm.
and then the equal vote suggested different weights of votes. You said
well,
deliberation of everyone.
Yeah, it wasn't through a voting process, but
I'm trying
yeah,
to
yeah.
abstract it to you. There is a bootstrap.
Mm-hmm.
Like how democracy decides to be democracy.
Right.
Someone has
Yeah.
someone has to make a democratic decision.
Yeah.
Decide start the country and say we'll have a democracy. So in the same way, it's like what weights are distributed is crucial. Particularly, this is almost like shareholders
Mm-hmm.
and different parties have different amount of shares.
Yeah.
Interest.
I think we get significant leverage here out of kind of a good faith assumption because everyone wants the same thing and they're all willing to participate in this process to get it. And so there is no sort of like competition or discord here. But I do agree that in general, like this is definitely underexplored, right? But like we are in some sense by fiat saying, okay, this is democracy now, like live with it, right? But yeah, in principle, there should be a better way of doing this like end to end, all based on the community perspective, as opposed to like researchers coming in and saying, okay, now like you have to do these things.
I just think that, it's a beautiful idea to say, well, instead of coming up with our moral rules, we just throw it to a democracy. But I sort of emphasize that even doing that, we assume some moral rules.
That is true. Yes, we're just kind of punting it one level up, I guess. Yeah.
So last week, Alex talked about like how they do like food allocation based on like some game theory stuff, like achieving like envy-free or like
Mm-hmm.
maximize social welfare and things like that.
Yes.
I'm just wondering how that fits into this picture, or they're like just independent things contributing.
I think they're pretty independent because if you consider his approaches, there are still some sorts of objective functions they want to maximize, right? So they are choosing some sort of like, this means fair, right? And they're trying to optimize that. Whereas we're just saying, we don't have any idea what is fair. We're just asking people to vote and somehow collect their opinions.
I see. So they're like, I was thinking that maybe you suggest something and then they take that into consideration and then do some reallocation and things like that. But apparently.
Yeah, I mean, there's definitely like opportunity for both of these things to come together a little more closely, right? Like maybe, yeah, there's some sort of like local optimization search you can do on these types of results that make them both kind of better, but yeah. Okay. So I'm very quickly running out of time. I did promise this could fit in the time allotted. And so I want to skip straight to kind of looking at virtual democracy in practice, right? So far we've just said Borda count is great, PMC rules not so great, and hopefully I've convinced you that this is, at this point, it's automated and democratized in the sense that it is from step 1 through step 3, just a way of getting predicted votes and then aggregating them into one final ranking. And it's democratized in the sense that we allow everyone in the system to kind of provide input through their model, right? I have not yet talked about if it's explainable or if it's effective. And these are things that we did in concert with HCI researchers. So they built a wonderful decision support tool that kind of implements this whole virtual democracy framework. And I want to stress that we're able to kind of hide and show recommendations at the behest of the people actually doing the work. So if they want the recommendations, they can look at them. If they don't, they can do it themselves. And the recommendations are kind of meant to like capture what is good about a particular allocation by highlighting particular features that they kind of stand out on, right? So if we look at this first one, it is kind of a very close drive. It is in an area with a high poverty rate, and it is in an area with a low income level. So these are all things that people kind of intuitively want in fair allocations. And also, I will say that we compared this to 5 months of historical data, and we see kind of very positive trends, right? Number one is we're allocating to way more recipients, because previously people had kind of forgotten about large swaths of the 400 plus recipients. And we also allocate more evenly, where the median went from 1 to 4, and the maximum went all the way down from 60 to 20. We also allocate more efficiently, like the average distance turns out to decrease, even though most people did not try to actually reduce distance for the volunteers. And we also allocate more donations toward recipients with lower income and a higher poverty level. And so here's a Lorenz curve on the left and kind of a distance versus fraction of allocations on the right. Basically, the closer to this 45-degree line, the fairer you are. And so our red curve is significantly better than the overall like human dispatcher's blue curve, right? Yes?
I have a question about baselines. So like what
Yeah.
you were saying initially about the way that these allocations happen in practice suggests that they're perhaps like very biased and like not, I mean, maybe sort of doing something that is not just like bad in a random sense, but sort of thoughtfully bad. And it seems like, I guess what I'm curious about is like how this kind of thing compares to say just random allocation, because at least the first 3 points, or at least the first 2 points, you would expect to be better on just random allocation if people are sort of like correlatedly only sending things that they're people that they know and trust or whatever. Do you have other baselines? Like, do you think that people before were like performing so poorly that like it's possible it could have just been worse than random?
Yeah, that's a good question. I am not sure. I do think that random would definitely do better on these first 2 points. I don't think it would do better on these last 2 points, because there are some recipient organizations that are in remarkably like wealthy and food-rich areas. They just exist there, and they perhaps deservedly get very few allocations, right? I forget if we compared to random. I think we did. I'm not sure if it's in the final paper or not, but yeah, I'll try to dig that up and yeah. Okay. And lastly, oh, sorry.
Yeah, in the interface you presented, you said you have these recommendations that immediately triggers thinking of like, recommender-based systems, and how is that different? Like, how did you compare to that? Like, I think maybe content-based filtering, where you say this item has the same features in your piece. Features that machine learning model is similar to another organization, so for example, you pull it up and put in the recommendation. Have you checked that? Did any comparison?
We have not checked that, but it's an interesting idea. I think it's definitely doable, right? Like the features I think they live in a small enough space that we can definitely do something like this, but yeah.
Yeah, if you're recommending movies, that would be your feature.
Exactly, yeah. Yeah.
So if you want to get the problem even more complicated, so in the very capitalistic world of online advertising, advertisement, they actually have online matching that keep aggregate capacity. So what happened here is that, I know it won't happen in Europe, okay, so it might be that one particular place is so favorable on everything else that they just get all the time because there's no history.
Yes.
Okay, so I just want to say that there are online matching algorithms. Basically, what you do is capacity matching, and there are online matching algorithms. So they are online. They make one decision after the other, but they keep some distribution. For example, I mean, advertisement is the budget, but
Yeah.
maximize advertisement. Are there a lot of constraints and subject to the budget of particular participants?
Yeah, that's a good idea.
And what you're doing is online matching, basically. It's a matching.
Yeah,
There are a
yeah.
lot of parameters, but
Yeah.
eventually it's a matching. And if you do it as an online matching, then you kind of keep the history in mind. That means that if one place already got a lot of assignment, maybe it's time for something.
Yeah, so we implicitly use this in some of the features, right? Like the number of donations, date of the last donation. So yeah, we were worried about this as well. And it turns out that it's not, at least on the historical data we tried, it's not like that big a deal. Like there are recipients who are categorically less fortunate than others, and they still don't get like an overwhelming majority of all donations, but yeah.
I don't know about this, but
Yeah, no, it's a good, yeah. It's a very good suggestion. Yeah.
Maybe it's in the slides. Something like top ranking,
No optimization at all. No, this is all just all voting.
Based on the beta vectors of the different stakeholders, do you have any idea of how much they consider previous donations and last data donation?
I have to check. I think people were pretty. They were, if I remember correctly, they were in the top half of the ordinal ranking of features that they cared about. So they cared about them quite a bit, but like not as much as something like poverty level or income level. I think those were often the highest. Yeah. And often distance was the lowest. Like people didn't really care about distance. Even the volunteers, some of them didn't really care. Okay, I've run way over. Apologies. I just want to leave on, maybe this is a good slide to leave on, basically talking about how people responded to this in in the human studies. Basically, it was very interesting to see that they were very receptive and kind of, encouraged by this democratic decision making, and also encouraged to interact more with this organization that so actively sought their feedback on this. And there's some quotes that are kind of nice about, this is better than what we had before. If people are getting forgotten about, that's bad, and we should get more input from everybody. So I'll end here, and thank you for being such a wonderful and engaged audience.